For my own adventure lab, I will be analyzing the parabolic motion of a volleyball serve. In volleyball, the motion, arc, and speed of the serve is crucial to the game, so I thought it would be interesting to look further into the physics of this motion I have created and watched thousands of times. I will predict the motion of the volleyball using a computational model using Newton's second law and the position formula, and compare it to the data I collected in Tracker of the observed motion. I will also observe the effect drag had on the ball as it went through the air, and the conservation of energy throughout the motion. Here I will use the energy principle, delta E equals work plus Q, which we will see is a change in energy equal to the change in kinetic energy plus the change in potential energy of the Earth. I found that drag does not have too much of an effect on the volleyball, but other things in the surroundings do, and that the energy principle would not be completely conserved in our chosen system. It would be negative. I will walk you through Tracker, the making of the computational model, and my final results. In Tracker, I tracked the motion of the volleyball in the positive X and positive Y direction. The origin of the axis was set at the ball's original position already in the air, so the ball's final position will be a negative Y value. First, I did all the initializing values. Ball mass, which is a standard volleyball, weighing 0.26 kilograms. The ball position starting at the origin, and finally I calculated the start velocity by taking the first couple X and Y values from Tracker, adding them respectively and dividing them by the change in time. Then, as always, delta T is an extremely small time step at 0.001. We then initialize some more values including gravity, kinetic energy, potential energy of gravity, and the unit vector for the y-axis. We then go into the while loop, which will make our predictions. Keep in mind we are doing two things simultaneously, finding all the energies as well as calculating drag. For time below 1.566 seconds, we must first define the initial energies. Then we will find the weight force and the drag force. I found the drag force through trial and error until the graphs were as close as they were going to get. You add those two values up to get the total net force. Now it's time to predict motion. Newton's second law and position formula iterate and predict the motion. Then the next few lines calculate the energy changes. We can then run the code and we get this. As you can see, this is the general motion a volleyball would take in a float serve. The gravity force, represented by the yellow arrow, is much greater than the drag force, which is represented by the blue arrow. We will talk about the two corresponding graphs a little later. If we look at the graph that does not calculate in drag, you can see that the data is very far off, especially towards the end. But drag does not have that much effect in the beginning. If we model the drag correctly, it should look more like this graph. There are many factors and reasons for discrepancies in this experiment. The situation was not ideal, so there was inconsistent wind, the camera angle was almost perfect, but there's a chance it was a little off, and though I have served many volleyballs in my life, I cannot correct for wind, so the ball did not travel in a straight line, but curved toward the camera. So we would expect the graph to be off by a little, if not a lot. But all in all, there's a marginal effect done by drag, and there are many things affecting the ball. Now looking at the energy graph, let's see what's going on. We will choose our system to be the ball and Earth. If we look at the energy graph from the code with no drag, we can see that energy is completely conserved because there are no outside forces acting on the ball. If we watch again when drag is calculated in, then we can see that the total energy is negative. This is because kinetic energy is being transferred out of the system. So the air is essentially doing work on the system when we calculated in drag. So all in all, there's a small amount of drag on the object, but there are many other factors that create discrepancies from our Tracker data. The energy principle is dependent on the chosen system, and when the system is only the ball and the Earth, then the total energy will be negative because of the work done by the wind.